can think in this way. Why they should, you want them to be closed. Okay, what is coverage? Coverage is like there is a random set S of x depending on the observation, and then you look at whether theta, the parameter, belongs there or not. The coverage is its expectation under theta. So given theta, its expectation. On the other hand, Bayesian's credibility is the same thing, expectation, but given the observation, not given theta. So here theta is random, here x is random. So it's completely different things. So they are both some kind of projections of this indicator, which really matters. The question is under, so they give some kind of half information about the indicator, and so they need not be close. But if they are close, then you have something to really good, because you have agreement between Bayesian and frequencies, and they kind of strengthen each other's, confirm each other, like endorse each other's evaluation. So that's always good. And in parametric problems, this happens by this celebrated theorem known as Bernstein-von-Mises theorem, which is also asymptotic normality of the posterior distribution. But in non-parametric problems, you can have discrepancy. So in curve estimation, for instance, Cox showed, this is D.D. Cox, showed that if you take a Bayesian credible set of some smoothness alpha in the optimal way, and then you construct the credible sets, then it can have arbitrarily low coverage. So they do not quite agree. So we'll call that Cox phenomenon, and then there are ways to address that. Basically, you have to modify your credible set. So you can do either undersmoothing, or you can inflate the original Bayesian credible set to comply with the coverage required. So that's a different thing, but the point is that in general, if you take as is, then it doesn't, these two don't agree, and that will call the Cox phenomenon. Now here we are interested in doing a Bayesian credible set for f of t0 and using the projection posterior. So we look at the projection posterior of f of t0, so we call that f star t0. That's the isotonization of f evaluated at t0. And then we have got a posterior, we have got a description also, we have cheap samples from the posterior, so we can easily construct a 1 minus alpha credible interval. So for instance, it could be taken as equal tailed interval or around its mean or median or whatever. So we can easily construct a 1 minus alpha credible interval. Now if there would be a Bernstein-von-Mises type theorem for this problem, so here the convergence rate is n power 1/3, not n power half. So that's why it's n power 1/3. So suppose we have some kind of Bernstein-von-Mises theorem that would probably read like this: the posterior for n power 1/3 is star t0 minus some kind of estimator that is used for centering at t0. This probability less than a number, given the data, converges to some distribution, let's call it h. In the parametric case, this is n power half, and that is normal. And the corresponding thing for the frequentist thing, this is the coverage. You have a limiting normal distribution in the parametric here. If this goes to the same h, then this two would be close for large n. So that is the agreement between Bayesian and frequentist uncertainty quantification. So if this happens, then we have the coverage issue solved. But does it happen? First, to answer that, we need to know what is the right choice of the centurion, because a lot depends on that. In case of in case of parametric, you take that the MLE and it works. You could take that as any Bayes estimate that works. But what is the right thing in this case? Well, the common estimator, usually it's a common estimator, and you take that as a common estimator is obtained by the isotonic regression problem. So you minimize this subject to the monotonicity of F, and the solution is the isotonization of these pairs, right?
What do you mean by common? Common between what and what?
The centering, you need a centering for this kind of thing.
Oh,
So
I see. Okay, the
it
F
cannot be
not-
F0, the
Yeah.
truth, because then it only weakly converges.
I
That's
understand.
not good enough.
Common between the coverage and the credibility.
Right.
I see. Thanks.
So, so you take some kind of familiar estimator as centering, and that's the first thing that comes to our mind, the usual estimator for F. But this estimator has, I mean, what is the property of this estimator? This has convergence rate 1/3, and if you scale it, then it converges to so-called the limit distribution is not a normal distribution. It's known as the Chernow distribution, and the Chernow distribution is the distribution of the argmin of a two-sided Brownian motion with a parabolic drift. It's well studied. It is symmetric distribution with tails sharper than normal. And the key proof in this, key technique in the proof is the so-called switch relation that allows you to write events like this. The slope of the greatest convex minor end greater than something in terms of argmin of this process minus a drift, a linear drift. So these two you connect. So basically what you do is you write this probability as some kind of functional of this process, and then you have some sort of, so this is some kind of empirical thing, local empirical process, and you have some Donsker theorem there that gives you a Brownian motion and limit. So that comes from there. So that's the usual thing for, but in this case, the estimator that we have there, in nature is its nature is a bit different from what we are using. So in order, we have to make them somewhat similar, otherwise it's not possible to deal these two things together. So we modify that estimator by looking at the corresponding sieve maximum likelihood estimator. So sieve maximum likelihood estimator is very much like the maximum likelihood estimator. So you minimize the sum of squares, but now not over all F, but over F of this form, where J controls the size of the sieve. So J goes to infinity as n tends to infinity at the appropriate way. So that's the sieve MLE. And the first thing we do is, there was no theorem on the distribution of this, but using the same kind of technique and some tweaking here and there, with under this choice that J is more than n power 1/3 and less than n power 2/3, with some tweaking of the techniques, we could show that it ends up with the same kind of limit distribution. That's the Chernow distribution. The constant that appears, this is the standard Chernow. The constant that appears is given in this way. A is sigma square divided by the density at T0, B is that, and the constant is obtained from A and B in this particular way. So that's exactly same as the distribution of the maximum likelihood. So that's very much similar to what we have in the posterior. So now the main theorem we can write in this way, that if this is unique, that the function needs to be strictly increasing at T0. If J is between n power 1/3 and n power 2/3, then the posterior distribution of the of FT0, the projection posterior distribution centered at the, now this is the sieve MLE, scaled by n power 1/3, given the data, converges to this distribution. It's the same C that appears there, times the random variable that appears is not quite what we have for Chernow, but instead this one. let's call Z1, this is W1S plus S square argmin. So that's the Brownian motion with parabolic drift. And Z2 is, now there are two independent Brownian motion. One of them is this W1 plus the parabola, and then you look at the argmin. So what you see is that Z1 and Z2 are dependent because they have a common thing, W1. And so this difference is not a convolution of, this individually they are Charnoff, but they're not independent. So it's not quite a convolution of Charnoff. It's somewhat more complicated than that. So this we'll call the Bayes-Charnoff distribution. So this appears as the limit. So what we find is that the limit is not the same as the one. But then there is, so that means that the asymptotic coverage is not 1 minus alpha. But then there is some interesting twist in it. The two have the same scale. And these two, Z or Z2 minus Z1, they don't have any parameters. So their quantiles are completely known to us. So we can recalibrate. So instead of starting with 1 minus alpha credibility, we can start with a 1 minus gamma credibility, and then try to see for what gamma will get back 1 minus alpha coverage. And that, well, we still haven't studied this distribution theoretically, but we did some simulation, and here is the table. So look at this thing, which is the thing that interests to us, the target alpha, I mean, it should be 1 minus alpha. It should be written as 0.05, whatever. So for that, 95%, you need to start with 92% credibility. And that's kind of opposite of the Cox phenomenon. We call that the reverse Cox phenomenon. That is, in order to comply in smoothing problems, in order to get coverage, you have to inflate the credible set to get the coverage at the target level. Here, you have to contract it, at least here, at this range. It's not always, if it's very low side, then like 80%, then you need 83%. But people look typically around this area. So that's something new that we haven't seen before. Yeah.
So the underlying truth F, do you have any assumption? What?
Yeah, the assumption is it's monotone and the derivative is positive there.
And every kind of function? Every function? No,
any function with that property.
But this is an interval at given t0. It's not, you're not fulfilling the whole.
At a particular point. It's pointless at a particular point. That's why we're talking about interval rather than bands. Okay, so that's I don't think I have enough time. Just maybe quickly. So the switch relation does not directly apply on this difference because this is also monotonized. This is also monotonized. So what you have to do is to split in two parts. This, and then individually you apply switch relations on. So you find some kind of joint distribution, and then to find their joint distribution, in each piece you apply switch relation. So the first piece gives you, asks you to look at a process like this, which is centered and scaled properly. It splits up into two independent local empirical processes actually. And the variation of the first process. So there are two processes come because there are one source of variation is the posterior and another is for which you apply a conditional Donsko's theorem. But then there's the second one that comes from the fluctuation of the function around the truth, and that's a regular Donsko's. And the second term there, that's just basically the second part of this thing. So they are treated together, and then you have joint convergence. So with playing with that, you can get through it. So these local empirical processes have Brownian motion limits, so that leads to this. and finally the targeted distribution. So how much time can I have?
5 to 10 minutes.
5 minutes?
5 to 10.
Okay, great. Okay, so that ends the discussion on credible sets.
That means that.
Now we look at the third aspect of this course, testing. Bayesian testing for monotonicity. Okay, how do you test a hypothesis? I mean, so part of the parameter space is script F, that is the space of monotone functions. So you look at the space of all functions, and then you put a prior, you get a posterior, and then you can compute the posterior probability of the part you are interested in. So that is the monotone, and that's equivalent to saying that these thetas are ordered. If the probability is too low, and lower than 1/2, let's say that's your benchmark, then you reject the null hypothesis in the Bayesian sense. Okay, so that would be the standard thing to do. And what are the properties you would want? With large sample, you want this test to be, to have, type 1 error probability, you want that to go to 0 uniformly over, well, you cannot have uniformity over all monotone because that's a non-compact. But for some reasonable compact subsets, you want monotone. And you also want universal consistency. By that I mean this following, that if you have any non-monotone function fixed, then the power at that should go to 1. So the type 2 error should go to 0 for any fixed thing. No assumption on smoothness or anything, it's just universal. And finally, for the uniformity you want is like this, that you want good power, right? So, but how good the power will also depend on how smooth the alternative is. If the alternative belongs to a holder class, or rather a compact subset of the holder class, then and I mean, what you want is under what condition the power should go to 1 uniformly. And for that, clearly, if you want uniformity, you cannot make that be too close to the space of monotone functions, because then you have interference with this. So the question is, how much separation you need in order to have that power go to 0. That kind of measures how accurate the testing is. So the smaller the separation, better it is. So, and kind of expectation is that it should be somewhat like the convergence rate at those class of functions. So that's what we want to do roughly, that we want put some minimal separation so that we have uniformly the power going to 1. The problem with this is that if you go by this, then a natural test, by going like this, a natural test would be just judging the posterior probability of this happening. If you go by this, the problem is that the first thing will fail. The type 1 error probability will not go to 0 because there may be some monotone functions whose neighborhood will contain non-monotone functions. So that's why this probability may not be very high, and hence you would reject the null hypothesis if you just go by this. So that's the standard problem near the boundary. So in order to avoid that problem, Solomon a few years ago, what he suggested is just enlarge this F before you calculate the posterior probability. So put a cushion around F and then compute the posterior probability and make your decision based on that. The Solomon enlargement is based on the maximum aberration. So you looked at the differences and The differences, so basically, ideally this should, when it's monotone, so if k is more than j, this should always be less than equal to 0, but he provides some cushion, so it's some margin, so allows some small aberration, and then it's enlarged parameter space, and then he proves that you can have the probability of this thing going to 1 if the function is actually monotone. So we'll follow the same approach, but we put a different blanket, different cushion around the truth, namely in terms of L1 metric. And this way we can, so Salman's problem is like if he uses his enlargement, so his problem is that it's restricted, first of all his method is restricted to equidistant predictors, and there was no universal consistency because he cannot handle things that are not appearing at those points. So there was no universal consistency, but by replacing his enlargement by another one defined through the L1 distance, we can bring back the universal consistency, and we have all other properties he established, namely the so we can take particularly this enlargement of size n power minus 1, right? So this is somewhat easier to implement than his procedure, plus the optimal separation that he gets, we also get, provided we put a prior on the number of terms. And if we don't put a prior, we don't get the optimal separation. That would be much easier to implement. We get universal consistency and nearly have good separation, but not the best, because this is the difference. So if you put a prior, you get the optimal one in power minus alpha over 12 plus 1. But if you don't put a prior, just put j like n power 1/3, then you get this separation, which is somewhat bigger than the optimal. But the difference disappears if your alternative is smooth order 1. So I think, yeah, the rest is numerical, so it just doesn't take much time. So we compared the Bayesian credible and coverage. In large samples, they are very close to the target. You see, 197.5, you get 97.4, like that. So coverage was done well, and for testing, it's a bit preliminary. So we considered these functions. Out of that, the middle two are monotone, and the other two are not. And the idea is that when it's non-monotone, you want to reject. When it's monotone, you want to accept. That's more or less happening, but of course, there can be some small. There would be some 5% you are allowing. So it's still a bit preliminary. So I don't want to exactly elaborate on this. We're still working on the testing simulations. So I think that's pretty much all. Thank you so much.
So any questions?
You emphasized in response to a question that you were estimating f only at one point, so you had intervals rather than bands, you said. Right?
For the credibility thing, yes.
Right. Can you handle multiple tests? Can you do bands?
I mean, one thing you can obviously do, if you have the pointwise band, pointwise intervals, you put them together, you get band. But that's pointwise band. So
Sure.
what you mean is whether I studied theoretically
Exactly,
the
a lot.
band. No, we haven't, because I don't think. Because this, if you look at the frequentist literature also, like the kind of distribution they have at the single point, also only have pointwise results. So it will need to extend this distribution theory substantially before we can even do that. So I don't expect this to happen too quickly, but maybe sometime in the future somebody can do that.
Have you tried anything similar with convex functions?
Oh yeah, that's a very good question. Yeah, that's something in our agenda, and but of course you cannot handle that using state functions.
Sure,
because
right.
State functions
Yeah.
will never give you convexity. That's a big challenge, because as soon as you go from state to some other function, some of the things we are doing just break down. So we have to find a way to handle that, but that's definitely something interesting that we'd like to do next.
Also, can you go back to the slide with the, you use the triangle inequality and
Oh, yeah.
the monotone
Somewhere in the
approximation?
beginning. So this is the truth,
Right.
this is the projection. We want to show this to a close. So first triangle inequality, insert the theta from where this came.
Yeah.
And this is the accuracy of, without any restriction, we still have some contraction rate. That's in fact, I mean, that's the optimal rate is still, it's only not monotone, but otherwise it's, in terms of accuracy, it's fine. And this one, by definition, this is the projection. So this is another point. So this is farther away than this. So this is smaller than this difference.
Even in the one norm, or am I miss?
So this is the isotonization.
Sure.
So this theta sequence and yeah, all norms, like it's not sum of squares only. I mean, this general, this is actually any, in terms of a function, you can have that. So all of them lead to the same solution. Yeah, that's important. So that's the generalized isotonization.
I had one more question. I didn't understand your answer about convexity, because a convex function is just a monotone decreasing function followed by a monotone increasing function, right? And the sort of new part of it is that you don't know where the change occurs, if any, right? You know, from one side
No,
sine of derivative to the other.
If you have steps, you cannot have convexity, right?
Well, the step functions themselves aren't going to be convex, but they approximate a convex function.
Oh, yeah, that's true.
Yeah, so I mean, I think it sort of just seems as if there's one additional level of complexity, which is to sort of locate the minimum of the function. And then, you know, then it's monotone on one side and monotone on the other.
That's not a problem, because all I can do is, like here, in order to do that, I put a
Put a prior on the location.
this restriction, like thetas are
Yeah.
increasing. There you just make this theta
Yeah,
sequence
make it a U-shaped
convex.
thing instead, right?
Then the resulting sum
Yeah.
will give you, but resulting sum will kind of give you the convexity.
Right.
But yeah.
I agree. It won't itself be convex, but it's approximating something.
That is true, but also the goal is to put up, the posterior should sit in the
Oh, it
parameter
should sit in,
space.
so you'd have to modify it somehow.
So if you allow that kind of enlargement, yes,
Yeah.
that's right. But I think the better thing is you want to achieve, to think like, I think one has to use a smoother basis rather than
that's
the
possible.
car ones. So.
Maybe following up on Jim's question, are there similar methods using projected posterior that address more general shape constraints
You mean
on the function?
Yeah, that's something, a long-term goal thing, but this is just the beginning of the investigation. So it would be, I would be speculating a bit too much if I say something. Yeah, that is the goal, that using this as starting points, we want to address other things. So for instance, we can already use the same idea for monotone, but in other contexts like density or some kind of censoring problems. But convexity, we have to think more whether, yeah, so especially if we can handle more complex spaces than plane intervals, then that would be an answer to that problem.
Okay, so let's thank Professor Ghoshal again. So we have freshmen